Hello friends, in this session we will discuss about electrode potential and how to measure it. First, let us see how does an electrode potential develop. When a metal ion is in contact with a solution containing its own ion, two things can occur. One, metal atom can move away from the rod into the solution, leaving behind electrons on the metal. Thus, the metal becomes negatively charged and the solution becomes positively charged. The other instance is when metal ion enters into the metal lattice from the solution. Thereby, the metal becomes positively charged and the solution becomes negatively charged. In both instances, a charge is developed on the metal that attracts oppositely charged ions in solution towards it, and thus an electrical double layer is developed on the metal solution interface. This equilibrium potential difference is the electrode potential. As can be seen in this diagram, we can see that the brownish red colored circles represent the atoms of a metal that is moving away from the rod into the solution. On the other hand, the orangish red colored circles represent metal ions that are moving in from the solution to the metal lattice. Single electrode potential is a measure of the tendency of an electrode to lose or gain electron and is the equilibrium potential difference developed due to the separation of charges at the metal solution interface when a metal is kept in contact with a solution of its own ion. The single electron potential depends on metal and its ion, the concentration of the metal ion in solution, and the temperature at which the system is maintained. Electrode potential is a measure of the tendency of the metal to get oxidized or its ion to get reduced. It is also called as reduction potential. A half cell cannot function by itself. Hence, it is impossible to measure experimentally the absolute value of a single electrode potential. What can be measured experimentally is the difference in potential between two electrodes. Hence, it became necessary to fix an electrode as a reference arbitrarily. The electrode so selected as a reference is the standard hydrogen electrode, and the potential of other electrodes are measured relative to the reference electrode. Standard hydrogen electrode, also called as normal hydrogen electrode, is assigned a potential value of 0 volt. It consists of a platinum wire attached to a platinized platinum foil dipped in an acid solution of 1 molar concentration. The system is maintained at 298 degree Kelvin and pure hydrogen gas at 1 bar pressure is constantly bubbled through the solution. To measure the potential of an electrode, it is coupled with standard hydrogen electrode through a salt bridge. The difference in potential is measured using a potentiometer, and the value so obtained is numerically equal to the potential of the electrode. If reduction occurs at the electrode, the value is positive, otherwise it is negative. An electrode is a standard electrode if its electrolyte concentration is 1 mole per liter. The partial pressure of any gas is 1 bar and the temperature is 298 Kelvin. The reduction potential of an electrode at standard conditions measured relative to the standard hydrogen electrode is called as standard electrode potential. E0 cell is equal to E0 cathode minus E0 anode. Arrangement of various electrodes in the increasing order of their standard reduction potential is called as electrochemical series. This picture represents an electrochemical series wherein various elements are arranged in decreasing order of their tendency to get oxidized. It helps to predict the relative ease of oxidation of different elements. As can be seen here, lithium, which occurs at the top of the series, is easily oxidized and is the strongest reducing agent. On the other hand, gold is one of the least oxidized metal. Fluorine gas is the strongest oxidizing agent. Therefore, necessarily, fluoride ion is the weakest reducing agent. The electrochemical series allows us to calculate the standard EMF of a cell by using the equation E0 cell is equal to E0 cathode minus E0 anode. If the standard reduction potential of cathode and anode is known, we can calculate the EMF of the cell. In this particular example, the standard reduction potential of zinc and copper is shown. Electrode with a higher reduction potential here is copper, hence it acts as the cathode, and zinc acts as anode. The value so calculated is 1.1 volts. Electrochemical series helps predict the direction of a displacement reaction. Metals with lower reduction potential will displace a metal with higher reduction potential from its salt solution. In the given example, since the reduction potential of copper is greater, it will be displaced by zinc from the solution. Any metal will displace any other metal that lies above it from its salt solution. Electrochemical series also helps predict if a metal can displace hydrogen from dilute acid. If the standard potential of an electrode is negative, they liberate hydrogen from dilute solution. Reduction potential of an electrode depends upon the concentration of the electrolyte and temperature. For a metal-ion electrode, it is given by the Nernst equation that states that reduction potential of an electrode is equal to standard reduction potential of the electrode minus RT by NF and the into ln concentration or molar concentration of the metal by molar concentration of the electrolyte. Since the metal is a solid, its value is taken as 1. Then the reduction potential of the electrode is equal to standard reduction potential of the electrode plus 2.303 RT by NF logarithmic value of the molar concentration of the electrolyte. Let us look at a problem. What is the electrode potential at 298 Kelvin of the electrode consisting of a silver rod dipped in 0.05 molar silver nitrate solution given the standard reduction potential of silver? The chemical equation is a very simple one wherein a silver ion is getting reduced to silver. The number of electrons involved in this case is 1. If we substitute these values in the Nernst equation, then we directly get the answer. The only thing that you have to remember is the value of R, universal gas constant, is 8.314 joule per Kelvin. Temperature is already given in the problem as 298 Kelvin. F value is 96,500 coulombs and N is equal to 1. Electromotive force or EMF of a galvanic cell at a given temperature is the difference in potential of two electrodes of the cell when no current is drawn from the cell. E cell is equal to E cathode minus E anode. Positive value of the EMF indicates that the cell reaction is feasible. If the value is negative, it means that the cell reaction is not feasible. For a galvanic cell with the overall cell reaction as given here, the EMF can be calculated by using the equation E cell is equal to E0 cell minus 2.303 RT by NF log molar concentration of the products raised to the power of their respective coefficients by molar concentration of the reactant raised to the power of their respective coefficients. An electrode whose conventional potential value is accurately known is called as a reference electrode. It can be coupled with any other electrode to determine the potential of the unknown electrode. As we have already seen, standard hydrogen electrode is a primary reference electrode. Secondary reference electrode may be either a calomel electrode or any other such electrode, for example, a silver chloride electrode whose value is given as 0.2224 volts. Let us look at the case of calomel electrode. It is an example of metal insoluble metal salt electrode. The metal in this case is mercury and the salt is mercurous chloride. The equation is shown here. The setup consists of pure mercury placed at the bottom of a glass tube. It is covered with a paste of mercurous chloride and mercury. The tube is then filled with differing concentration of KCl solution. The concentration of KCl may vary from 0.1 normal to 1 normal, or the solution may be a saturated solution of KCl. This solution is also filled into the curved side tube which is used to connect this electrode to other electrodes. A platinum wire sealed into a thin glass tube containing a little mercury at the bottom serves to make electrical contact with the external circuit. The electrode potential depends upon the concentration of KCl used. As can be observed, as the concentration of KCl increases, electrode potential decreases. When the concentration of KCl is about 0.1 normal, electrode potential is 0.3338. When the concentration of KCl is 1 normal, it is called as normal calomel electrode and the electrode potential value is 0.28. When KCl is a saturated solution, it is called as saturated calomel electrode and the electrode potential value is 0.2415. A fuel cell is also an example of a galvanic cell in which energy of fuel oxidation is directly converted into chemical energy. The difference from the traditional galvanic cell is that, unlike in the galvanic cell, where the reacting substance are stored within the cell, in the case of a fuel cell, they are fed continuously from the outside. The most simple and the common example is hydrogen-oxygen fuel cell. It consists of porous graphite electrodes impregnated with platinum catalyst. An aqueous solution of NaOH or KOH is placed between the electrode. The hydrogen and oxygen are fed into the anode and cathode respectively at high pressure, around 550 atmospheric pressure. This gas bubbles into the alkali solution through the porous electrode and a reaction takes place wherein 2 molecules of hydrogen reacts with 1 molecule of oxygen to form water. The energy so released is converted into an electrical energy. We come to the end of the session. Thank you.